All right, good morning. Come on, guys.
Good morning.
All right. I know I'm between you and the end of the session, so I'll try and keep it as entertaining as possible. If you don't ask me questions, I will. All right? So what am I going to talk about? A little bit of background. I've been with IBM for 26 years now, and every 5 years or so, it looks like I have a new job. So I've been in this new job on quantum for about 4 years now. And my focus has primarily been, in addition to having a background in quantum mechanics and computer science, I started getting into cybersecurity. So my focus has been on the cybersecurity implications of quantum. Now, how many of you know what quantum computing is? Good, 2, 3 hands, which is good because I will start with what is quantum computing and then where are we with quantum computing? Why is it real? Because many people still think that it is somewhere out in the future, may or may not happen, something that you read in comic books sort of stuff, right? But I'm just going to show you how real it is. That's one. Second is more here and now, what are the cybersecurity implications of that, right? And then what can we do about it? That's primarily going to be my discussion here. So one thing I want to be clear is when we start looking at computing and the future of computing, the way we look at it is it's not just bits or just your classical computing now. We have CPUs, which are bits, and we have GPUs that we call kind of neurons, and then you have qubits that are quantum computers. These three work together. So it is bits, neurons, and qubits is how we look at it. And these three don't operate, well, they do operate independently, but the power of the future of computing is in actually all three of them collaborating together and working on a specific workload to help drive a desired outcome, right? So we are not looking at quantum computing as something that operates independently by itself. As far as I can see now and foresee in the future, quantum computers do not operate on their own. They do need a classical counterpart. They always work in conjunction with a classical computer, right? So in that context now, let's get into what is quantum computing. There is probably one geeky chart in this, right? Other than that, I'll try to keep it as consumable as I possibly can, right? So what we focus on at IBM on quantum computing is we focus on bringing useful quantum computing to the world and to keep the world quantum safe. Now, I particularly made the second part colorful, so I can also add a line that says, my focus is on the colorful part of the mission statement, all right? Now, you're not laughing, man, this is a tough crowd here. All right, so this is the only geeky chart. How many of you know about logic gates? Something you studied in high school, maybe, yes, some hands go up. So, classical computing, at the end of the day, operates on a certain set of gates, and or not, right, and so on. The same principle applies in quantum as well, and there is a reason why I call out this gate philosophy, to show that there are fundamentally certain gates that you need to operate to execute a desired outcome that you're looking for. In the case of classical, it is addition, multiplication, movement of data, that sort of stuff, right? Similar stuff happens in quantum as well. There is a Hadamard gate, a Toffoli gate, so on and so forth. I'm not going to go into any of the details, but suffices to say that the same paradigm applies in quantum as well. And they two work together to execute an outcome. The second thing that I'll call out is, I kind of hinted this already. If you have bits in classical, you have qubits in quantum computing, right? Similar. Now, similar but yet entirely different. The difference is in this. If you look at bits, they're like an on-off switch. They're either 0 or 1, right? Whereas if you take a qubit, it's like a dimmer switch. It can have a value of 0, or it can have a value of 1, which is the other end, or any value in between. So there are technically infinite set of values that it can take. And that's the big difference. The other one is it can have those values simultaneously, which means it can be a 0 or 1 or anywhere in between at the same time. That is difficult to comprehend, but that is nature. That is what quantum computing is. And when you begin to manipulate and operate with those principles, you find that you have significantly more number of data values that you can represent. So if it is 0 or 1, it's one or the other, right? Whereas if you look at 0, 1, or anywhere in between, you have an exponential set of values that you can have. Therein lies the capacity or the strength of quantum computing, right? So pretty soon you will find, I think there's a chart later on that kind of explains this better, so I'll hold off on that. So that's about all the fundamentals that I want to leave you with on quantum computing. If you do want to have an interesting cocktail conversation and show that I do know something about quantum computing and wow, somebody else you're talking to, then a few tidbits for that. This dimmer switch analogy is an excellent one that you can use. The other is, at least in the quantum computing technology that we adopt, which is called superconducting qubits. The qubits are at almost absolute zero temperature, which is colder than outer space, because you are operating with fundamental particles that get agitated pretty easily. Noise, sound, electromagnetic interference, vibration, temperature, all of them will upset it. So you have to cool it down to the lowest possible temperature you can. I think it's about 15 millikelvin above absolute zero, which is very, 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 very cold. And then that's when you operate on it. That's another technique that you can use. The last piece of information that I'll leave you with is, while quantum computing can do a number of interesting things, it sucks at doing multiplication. You can do multiplication in classical computing in a nanosecond or even sub-nanosecond. You think about doing multiplication in quantum, it takes a long time, in milliseconds, if not more, again. So what can you do with quantum computing, right? The simple way to understand the chart behind you is to say, look, there are problems that classical can solve, and there are problems that only classical will continue to solve. You will never expect to see quantum computing doing your payroll or customer call management or any of the other standard applications that you typically see. There are certain applications that classical solves well, but quantum solves much better. Case in point, some AI problems, detection of fraud, right? Or anti-money laundering, fraud management, that sort of stuff, optimization. These are all things that classical does kind of well, but quantum can do much better. And then there are certain class of problems that classical simply cannot solve, and quantum solves much better, or quantum can solve, right? Obviously, it's better if it cannot be solved by classical. And factoring is one of those problems that classical cannot solve, but quantum solves better. Hold that thought. I'll come back to it in the second half of my discussion. With me so far? All right, I see a few nods. Good. So what can it do? Double click on this a little bit. I've already touched on this. I'm not going to go into this a lot more detail. You can look at what's on your left-hand side as a set of mathematical algorithms that are fundamentally solvable in quantum. And what's on the right-hand side is where you apply those to really drive some business value, right? So you can see that there is a whole set of industry solutions that quantum can solve, and I dare say is solving, using the primitives or the fundamentals you see on the left-hand side. So you can pick your favorite industry and go into any of these use cases. The other way to look at this is optimization is one problem that quantum solves. AI, in a way, is another problem, or quantum machine learning is another problem that quantum solves well, because at the end of the day, AI is about identifying patterns in a sparse matrix where there is very little data. Can I go and find a pattern, right? Quantum is good at doing that, right? So some of these fall into that as well. Now, for those of you who are doubters, right, I just want you to take a minute to look at this. The progress in quantum computing over the years. You'll see that even though, in the last 20 years or so, from 2006 to 2025, you will see that there is a heck of a lot of progress made in the last few years than in the years, in the previous set of years that are put together, right? And I'll quickly give you a walkthrough of what the progress looks like, and then I'll take a minute or take a pause to look at some of them in depth, right? Now, we have been a leader in this space for 40 years. We started working on quantum computing almost 42 years ago. But I'll just take you through the last 10 years, right? In 2016, we put the first quantum computer on the cloud, all right? I don't know if many of you know about that or not. And then we also released the following year an open source SDK for anyone to go and work on quantum computers. It's available today in a much more robust form, and you can go and play with it and begin to learn a lot by actually doing it. And then in 2017, we also said, look, it cannot be an individual sport. It has to be a team sport. So we began to put together a quantum network that consists of enterprises, academia, national labs, and other interested parties coming together. I think I have a chart later that talks about this a little bit more, but we began that collaboration almost 8 years ago. And to date, we have over 80 computers, quantum computers, on the cloud that you can use. And there are over 600,000 users in the community around who have been using this. And the quantum network I just talked about that we started in 2017 has about 280 or so members right now. And across the world, there have been over 10 million learners who have used quantum Qiskit to learn about quantum computing. So this is not something that is kept in a closet or kept in a research lab. This is very much out in the open, and people are adopting and following it. So I talked about the quantum network, right? I do want to pause here for a minute for you guys to scan through this set of icons here to see if you recognize any of them. The one in the middle of the top column there is, top of the middle column there is Cleveland Clinic, which is not too far from here. They are one of the, I think, 8 or 9 instances where they have a quantum computer on their premise. Interestingly enough, it is in their cafeteria, so you can go and take a look at it even if you don't want to go in for anything else. It's an interesting observation to see how they have displayed that. RPI in Rensselaer Polytechnic Institute in New York, and there are several others that have a quantum computer in their own premise. So in addition to the 80 or so that are on the cloud, there's about 8 or 9 that are on custom installations or custom on-premise installations. So what are they doing with this, right? What they're doing with this is there's a set of activities or problems that they're solving. And before I get into that, you need to know, so how does one go about measuring this, right? And so I'll just give you 3 snapshots to give you data points on where we are today. In 2022, we crossed the 100 qubit barrier, meaning there is a chip that has 100 qubits or more that is available for folks to do computations on, right? Now, why is this 100 qubit barrier important? Because at about the 100 qubit barrier, which is part of this, I think we have named our chips after birds. So you will have Eagle as the current one. Heron is the current one that we have. In 2022, we released the Eagle processor with 127 qubits. What does 127 qubit really mean? Just for comparison, if you had 30 qubits, it's about the size of, it takes about 17 gigabytes, or it can represent 17 gigabytes of data, right? So 30 qubits is about that. 49 qubits, given I'll give you one more thing. 31 qubits, right, will require 2 of these laptops because of the exponential nature of the qubits themselves, right? So if you have 49 qubits, it'll take up the Frontier supercomputer memory capacity as to how much data Frontier can represent. We can represent in 49 qubits. With 100 qubits, you are exceeding or touching the connected capacity of all classical computers on Earth, right? And where we are today is 156 qubits. The Heron processor I talked about is about 156 qubits. Now, this gives you a feel for the amount of data that you can represent, and that is where the power of quantum comes in, because classical stops at visualizing certain data beyond a certain point. You cannot visualize three-dimensionally the molecules. You cannot, the materials. You cannot model certain things beyond certain capacity. I earlier alluded to the fact that classical does certain things well, but quantum does better. One of them is optimization or fraud detection. Any of those problems is actually a multi-objective optimization problem. You want to balance your portfolio against a set of parameters. You want reduced cost, increased returns, relatively flat against the market fluctuations, and you have to balance that against the market indices, weather, geopolitical activities, blah, blah, blah. Right? There's only so much you can do in classical. So you make assumptions and operate within that, and we are reasonably comfortable with it because that's all you have. With quantum, you get to do a lot more. You have given, that's the representation. That's where the value of, or the capacity of the data that you can evaluate becomes important. Hence, the number of qubits that you have gives you the ability to solve more and more complex problems that you can only imagine in classical. Now, why are we able to do this work so well? This is a little bit of a plug for IBM. We have been in semiconductor business for about 60 plus years, if not more. And the consequence of that is, and you may know that we have a fabrication plant, 2 nanometer fabrication plant in upstate New York, and we have been in that business, like I said, for several decades. The consequence is that we are the only ones approaching quantum computing as an engineering problem and not as a research problem. What do I mean by that? So there is an issue, for example, all these quantum computers have this notion of noise, right? The qubits that are kept at almost absolute zero are manipulated by microwave signals to do what you want them to do. But they don't want to behave. They will decohere. They will reset from their zero state. And so you have to reset them again every so often, right? That is called a coherence issue, right? And we can call it as noise, you can call it as error or a combination of it. So these are fundamental problems that exist. Now, these problems are not new. Your classical computer, your laptop, your Windows machine, Mac machine, they all have an error correction chip inside them that we've just taken for granted. If I remember right, the name of that is Hemming error correction code, if I remember right. That was discovered years ago, right? So it is known that these semiconductor devices will have errors, and you know what's causing them, figure out a way to correct it and move on. That's how your laptops and computers produce the same result repeatedly again and again and again. We are not yet at that stage with quantum. We are at the stage where we know what the errors are. I'll tell you when we intend to recognize the errors and correct them, but the point is that is where they are, which means that you have a problem, you need to know what the solution is. So there is theory first. Then you say, hey, can I take that theory and implement it as a proof of concept, a pilot, a prototype in my lab? That is a research problem. You take the theory and say, can I create a solution for it in the lab, in a controlled environment? Yes, I can. Then it becomes an engineering problem where you take that and say, now that I have a proof of concept in the lab, I want to take that and build it into the chip, manufacture it at scale, make it work in unconstrained environments. That is what engineering problem is. So when I say that we are dealing with this as an engineering problem and not as a research problem, I mean that we have solutions that we have proven in the lab that we are now scaling out. That is why we are able to produce a new quantum device every 17 days if we have to, in order to correct whatever we find. So a combination of the expertise we have in nanometer level fabrication combined with our ability to churn out these chips as an engineering problem gives us the ability to make measured progress, right? The next year, we wanted to show utility, right? So that was about getting to 100 qubits. Utility is about saying, I can solve a problem accurately, right? And at scale. And I'm not going to go into the depth of this except to call out a couple of data points here. We demonstrated this with a 127 qubit Eagle chip and 2,880 gates. That's what we needed to demonstrate that there is a repeatable utility value and we can solve a problem accurately, right? And all of what we talk about is published in refereed journals, so it's not us making any of this up, but it is referenceable as well. The next thing we said was, okay, that's 22 and 23. Now, in order to get to scaling out beyond that, we cannot look at it as quantum computer alone. It has to be done in conjunction with a classical computer. So you take, any of you are familiar with workloads that you deploy on the cloud, right? So take a similar pattern. You take a workload, some part of that problem or workload is best executed on a CPU. Some of them may be better executed on a GPU. Some of them may be best executed on a QPU. The challenge is figuring out which part does well where, and then using that particular component or chip to make that happen. That's what essentially quantum-centric supercomputing means. It means it's a hybrid computing architecture that leverages classical and quantum, not classical or quantum, right? So you move from one versus the other to one plus the other, right? That's the fundamental notion. This goes back to my very first slide about bits, neurons, and qubits. They all work together, and that's the best way to solve any problem. And we demonstrated this in collaboration with Riken, which is a chemistry research facility. And here we used a workload that ran on Fugaku, a supercomputer in Japan, and on the quantum computer Heron-based quantum computer that we have, to show that there is significant demonstrable value in this quantum-centric supercomputing model, right? Now, before I go into where we are today, any questions on this so far? I know I've been rambling on for a bit to sort of establish the context and background. Any questions on this so far? All right, I am thrilled to see that I'm absolutely clear, as always. So you may say, fine, I kind of get all that, right? Or I believe you, but then where is the proof point, right? Who is using this today to make any useful value out of it, right? Now, there is nobody using it in production, right? I'll tell you that because it's emerging technology. However, about a month ago, HSBC put out a paper. They are one of the quantum network partners. They put out a paper saying that they executed, trade execution strategies for, I think it was around bonds, where they found that their quantum-based model produced 34% improvement in trade fill estimates. Now, 34% in billions of dollars being moved around or fill orders being made is significant. Soon after that, almost days after that, Vanguard came up and said, hey, we have been working on this as well, and we found that in fixed income asset portfolio optimization, we have seen that quantum gives us better results than classical. Then Wells Fargo came along and said, I've been doing some time series analysis. where in time series, typically resource consumption is a huge issue, and we said we are finding that quantum is more frugal than classical in this. So these are just 3 recent examples, but there are many more that are being done. But almost all of them, right, are in their internal experimentation stage. And they're coming out with proof points so that they can learn and see how they can apply this, right? Now, let me switch to the next part where I do want to talk about the here and now of this. I said I'll talk about quantum computing and then the cybersecurity implications of that, right? This is where that is. Remember I talked about one problem that quantum solves that classical cannot? Anybody remember what that is?
Multiplication.
Sorry? Multiplication. Kind of. Multiplication is one that quantum does poorly and classical does better. But in my Venn diagram chart, I had factorization, which is reverse of multiplication, right? So if I gave you a number 65 and say, give me the factors for that, please, you can easily come up and say 13 and 5, right? However, there is really no algorithm to arrive at that in classical sense. There is no formula you can apply other than brute force to come at it. And this fundamental, and this is called factorization, by the way, and this fundamental mathematical problem is what we rely on for all our cryptography. Now, I mean, this is a cybersecurity perspective, so I'm sure you know about cryptography within the context of cybersecurity. Still, a basic primer, 2 types of cryptography, synchronous and asynchronous. And simplifying this, synchronous is for data at rest, and asynchronous is for data in transit. Asynchronous is using these protocols that you see, RSA, DSA, Diffie-Hellman, ECC, etc., right? Almost, well, all of them are based on this factorization problem. The fact that if I give you a large number, a 637-digit number that you see as RSA 2048, and I say, go find me 2 prime numbers that you have to multiply to arrive at that, you can do it, I can do it, a supercomputer cannot do it. And it is based on that assumption, premise, is what all the cybersecurity protocols are based on, or encryption protocols are based on. Simple problem that cannot be solved by classical computer. However, in 1994, Peter Shor from MIT, without even having a quantum computer to work with, theoretically figured out, oh, I can solve factorization by creating an algorithm. And he did. So there is an algorithm that exists. When executed on a quantum computer, it is capable of factorizing these large numbers. In other words, all of today's cryptography, or much of today's cryptography, will be broken when a quantum computer of sufficient scale and capacity becomes available. We call that a cryptographically relevant quantum computer, right? So the simple problem is our assumption that there is no solution for factorization, and therefore I'm going to use that as the fundamental underpinning for cryptographic algorithms, more precisely asymmetric cryptography, is broken, right? And you may say, wow, that seems scary. So when is that going to happen, right? When a quantum computer becomes available, yes, somebody can use it and break that, right? Now, just to rub it in a little bit more, right, and to scare you a bit more, what does it mean when asynchronous cryptography is broken? Every digital communication that you send and receive is likely to be compromised. I can masquerade as you. I can create fraudulent transactions and you won't even know it. And you know, Wes mentioned, if I remember right, the threat actor doesn't break in, he logs in, right? That's what's happening here. I will be able to log in as you. You wouldn't know it, nobody would know it until something really bad happens later on, right? So essentially, this is really bad. So you say, so I do have some time, because you said when a cryptographically relevant quantum computer is available, that is when somebody can break in. Yes, absolutely. Stuff to the right, right? We don't know what that Q day is. It's not like Y2K where you knew when that was going to happen. This is something that will happen sometime in the mid-2030s, is what we believe, right? So you don't know when it's going to happen, but you know it's going to happen. And when it happens, all the stuff you see on the right-hand side will happen. So you say, well, okay, so I still have what, maybe 7, 8 years? I'd say think again, because what's happening today is what you see on the left-hand side. Motivated bad actors are exfiltrating data as we speak today. Whether they're sensitive or not doesn't matter. Data is being exfiltrated, with the expectation that sometime in the future, when a quantum computer becomes available, I can apply a quantum computer to the data that I have and decrypt that and then see what goodies I have. How many of you know of this TV show called Storage Wars? Few, right? Where you go and bid on a locker that you kind of sort of know what may be in it, or you probably don't know what's in it, and say, $5,000. And then you go and figure out what's inside. And if you find a good heirloom, something there, or a signed baseball or a guitar that's worth something, then yes, you have hit the jackpot. Same thing can happen on the dark web with respect to data that has been harvested. I'm exaggerating this to make a point, which is motivated actors have data that they've exfiltrated, mostly nation states. They've exfiltrated the data with no hope of breaking it today. They don't want to break it today. They'll wait for years down the road to figure out what they have. And you and I, if we want to do it, we can also offload the data and then put it up on the dark web and sell it for some money later on, right? Possible. So my point is, this is something to watch out for. And as you very well know, we are not confident today in that our data is secure, not because nobody can exfiltrate it, but because even if they exfiltrated it, there is no way they can read it. That is how, so data is being exfiltrated for a variety of reasons, right? But they can't read, and that's why we are happy about it, right? But here, that is going to be broken. So that is something I want you to sort of internalize. Is something being done about it? Yes. In 2016, NIST started a competition to figure out, hey, what are the solutions out here? Who can produce algorithms that cannot be broken by classical as well as quantum? 84 submissions came in, 4 of them were selected. For standardization, 3 of them have been standardized, and interestingly, 3 of the 4 came from IBM, and then subsequently, the 4th guy also joined IBM. So we have, and these are the 4 algorithms, or 3 algorithms that have been standardized, and they have asked for a second round of algorithms as well that are a little more performant, or that are form factor oriented. So the bottom line is, yes, there is solution available. Post-quantum cryptographic algorithms are available today that one can begin to incorporate into your existing systems so that you can begin to protect what is happening, begin to protect your existing systems. However, data that has been exfiltrated, if the horse has left the barn, if the train has left the station, whatever analogy you want to use, there is no bringing it back. What is gone is gone. However, not all is lost. You only need to be concerned about, is that data that might have been exfiltrated valuable over time? Credit card information, no big issue, right? You can always change it. Its life isn't very long, and they're not breaking it today. So the point is, patent information, drug discovery information, anything that has value over the next 7 years or after the next 7 years or so is where you have to watch out. So the takeaway is, identify your crown jewels and make sure you're protected. The government has put out some timelines. I'm just giving you one of the timelines from CNSA that says, look, anybody who wants to do business with the federal government, you better be quantum safe by 2033. And they've even said which means that here are the other milestones based on that. If you have to meet 2033, you have to meet these other deadlines. Several other governments around the world have done the same, right? Now the question is, we are sitting in 2025. You have about 8 years. When was the last time we ever looked at what cybersecurity, what protocols are being used anywhere in our enterprise? Never. We haven't had a need. How many of you remember the log4j problem that came up in December of whenever, 2017, 2018, right? We scrambled around. We didn't know where all log4j was being used. So it scrambled around, and crazy enough, it happens, during December, if I remember right. So you're waking people up during Christmas holidays, asking them to go look for this, and then it took months to really figure out what that is. This is several orders of magnitude more complex than that. Where are we using cryptography within our enterprise, not just in our custom applications, but also in applications that all the third parties are providing us with? So you look at the supply chain, software supply chain, and say, how do I make sure everything in the software supply chain is quantum safe? That's where the problem is, right? With me so far? Are you scared enough? Right. So that's the reality of one of the negative implications of bad actors using quantum, right? Now, why do I think it is real? Why do I think it's going to happen in 2033, right? This is IBM's point of view, and based on where we are today, plus based on what we have read so far as well. So what we put out in May of this year, we have a roadmap that we have published that you can go and look at it. It's a quantum roadmap that we have put out on our website. You can go look at what we have said since 2016, 2017, or even before that. And we have been hitting every single one of them because, as I told you, we are looking at it as an engineering problem. And so we have solved it in the lab earlier, and now we are trying to scale it. So we know exactly what it will take to get there. So we are pretty confident about it. Based on that, we are saying that we will reach what is called quantum advantage in 2026, which means a quantum computer will solve problems better than what classical can, right? Now, this is what I've already shown you some examples of this with HSBC and Wells Fargo and Vanguard, right? So there are emerging solutions, but we will have a definitive, repeatable problem that we will demonstrate next year, right? That is an inflection point because there are certain techniques that we are going to have that we will demonstrate that will show that this is important. And here is what a section of our roadmap looks like. And I'll just bring you to this part. I think Nighthawk, if you look at it, we are going with Nighthawk, is the next bird or next name of the chip. So we are at Heron, and we'll go to Nighthawk, which has got 120 qubits, and it'll support 5,000 gates. Remember, I told you to remember that for the chemistry example, or the one before that, we had 2,880 gates that we used. So this one has 5,000. Then every year, we're going to increase that from 5,000 all the way to 15,000 by 2028. So essentially building up the capacity of these. And we also are not going to look at growing. If you want 10,000 qubits, we are not looking at a chip that has 10,000 qubits in them. We are looking at integrating or modularly interconnecting maybe 3, 4, 5 of these chips together, so you get to a total of 10,000, right? So there is form factor of that involved in as well. So that work happens, and you will get up to 15,000 gates that we will have, and 120 qubits, right? After that, we said we will reach fault tolerance in 2029. Fault tolerance means, remember I talked about errors? We have the ability to error correct in 2029, which means that similar to the Hamming circuit I talked about in classical machines, we'll be able to put forth something that will correct this. Now, some of you may have caught this in the news the last few days, where IBM and AMD said, hey, we just figured out that we can apply commercial off-the-shelf AMD chips to do error correction which will help us get to fault tolerance. So there are errors that occur. You need to figure out a way to correct them. And instead of having to create chips that will help implement that, in collaboration with AMD, we have figured out that we have commercially off-the-shelf chips that we can use, which means we can do it at a ridiculously inexpensive manner. And it left-shifted the entire schedule by about a year. My point is that there is a lot of work happening as we speak. We announced this in May. At that time, we didn't know about the AMD work, so the schedule gets left-shifted consistently. That's a takeaway. So 2029 is where we believe we will get to fault tolerance. What does fault tolerance mean? It means that the next set of chip from Nighthawk to Starling, when we will have 200 logical qubits. And take this, 100 million gates that you can operate on, which means you can solve a large problem, significantly large problem, compared to the 2,880 I showed earlier, to the 15,000 we will have, couple of years from now. And guess what? Sorry, went the wrong way. By 2033, mid 2033, we will have Blue Jay, which will have 2,000 logical qubits, which will have a staggering 1 billion gates that you can operate on. So you can solve a significantly large, complex problem using quantum computers during that time. Are we approaching a cryptographically relevant quantum computer by that time? You're within spitting distance of that when you get to that. Now, RSA 2048 requires a large machine to solve. RSA 1024 requires significantly smaller machine to solve, right? So don't quote me on this, but just for reference purposes, when you're at Blue Jay in mid-2033 with 2,000 logical qubits and 1 billion gates, you should be in the vicinity of solving RSA 1024. Right? Now, all that we need are a couple of inflection points, couple of advancements to left shift it. Right? Then you're in real trouble. Now, given this is all about data center, I thought I'd leave you with this, which is we are building a data center in Poughkeepsie, or expanding our data center in Poughkeepsie to have these quantum systems that we are beginning to establish. I already talked about 80 systems that we have on the cloud. Most of them are sitting in Poughkeepsie, and now we are beginning to install system 2s and system 2s where we can interconnect these together, and you will see that this is real. This is not a PowerPoint magic that I'm showing, but this is really stuff that exists today. All right? So that's pretty much all I wanted to cover with you today. Any questions? Yes, sir.
Yeah, I'll make an assumption. So GPUs that are used now in the data center, if we were to move to quantum computing, will that reduce the size of the data center?
Will that reduce the size of GPUs?
Of the data, because now you're moving to quantum. Now, are we going to still require all these huge data centers?
Well, you will require, remember I told you that your workload is broken up into what is appropriate for CPU, what is appropriate for GPU, what is appropriate for QPUs, right? And quantum doesn't solve all the problems that GPUs and classical typically do. However, there are certain class of problems that are now typically executed, AI-related problems that we get to that are typically executed on GPUs. You find that they're likely to be executed on QPUs. Will they result in a reduction in data center? I do not believe so, but it's speculation at this point. Any other question? Yep.
Have you solved your form factor problem for a QPU inside of the data center yet?
Have I solved a form factor problem of a QPU inside a data center? This picture does show that we do have racks of quantum computers. So what you see on the picture is a real rack that exists, that if you visit Yorktown, for example, you'll be able to see. So we know what it takes to install them. Yes. I don't know if it is a form factor problem or not, but we know that we can install racks and racks of these system tools.
How much does a quantum computer cost?
To own or to use? To own, it's an inordinate amount of money because right now, again, it's very expensive to have an on-prem setup simply because of the first, the refrigeration that is needed to cool it down, plus all of the supporting electronics that you need to have, that you need to support to operate that. So owning your own, like Cleveland Clinic does, is primarily for research purposes and an early investment. I wouldn't go there. But to use it, you can use it for free, technically, if you want to learn Qiskit. But then if you want your own dedicated time as an enterprise, then we have a certain pay-as-you-go type of plans that you can buy into. I'm just throwing some numbers out. I don't remember exactly what the numbers are right now, but you can commit to using up to $1 million for over 2 years or something like that, and you will get your time. And along with that comes help. Subject matter experts who will help you with identifying use cases that you can try and experiment with and solve. You don't want to waste your $1 million of timeshare on a quantum computer. We'll help you with identifying algorithms and solving them.
Yeah, so a rough order of magnitude of cost, right? A zetascale computer for 200 GB200s costs you about 20 B to put in 127,000 GPU cluster, right? So if I buy one of those and I want to hook it up to one of yours, how much is 4 or 5 of those units cost?
Not my forte. I have no knowledge. I don't want to BS you by giving you a random answer, but I can, if you can drop me an email on that, first I can pass it on to somebody who understands the question and can answer it.
What percentage of the total power consumption needed for cooling?
It's an interesting question. Everybody thinks that power consumption for cooling is enormous, but it is not. Because refrigeration has come a long way, and this is cheaper than what it takes to cool down, interestingly enough, the GPUs, because they generate heck of a lot of heat. Here, a QPU doesn't generate heat because you're not doing a lot of math with it that generates heat. You want it to remain at a cool temperature. So I believe that 150 watts is what it takes to keep the temperature cool once it has cooled down. I do not know what it takes to get it down to that level first. All right, I see my friend standing up, which is an indication that I am out of time, so sure.
On the algorithms, quantum computing proof, the ones that NIST adopted, have we, two questions on that. Have we assessed the computational power that needs to be embedded in devices to run those algorithms, the potential impact of them on devices that will have to run them instead of running RSA 2048, for example? Is there any comparison on that? And second, how long they will be quantum compute proof? How many years we expect them to survive, considering the progress we are making on quantum?
Okay, so two questions. The first one, when you say you want a comparison with what? I didn't quite catch the comparative part.
Today, we have processors for example, in our products that have to encrypt and using RSA 2048. I want to know if we have an idea of the difference in computational power for
Good question.
Okay.
Okay, so difference in computational power needed for the algorithms, classical versus post-quantum cryptography algorithms. We have actually, if you're interested, I can send you a link. We have done some work on that. So has Open Quantum OQS, whatever that stands for. There is work that has been done by NIST, OQS, and us to show these algorithms that we have chosen. So there are 4 algorithms. Couple of digital signature, couple of key encryption algorithms, and they all have different key values that you can have. So they have different variations, permutations, and combinations of how you can use them. So we have a tabulated set of, if you use these values in these curves, here is what the performance characteristic is. So there is a performance index that has been published. So you can use that to compare in your environment what classical performance is versus what quantum PQC algorithm performance is. There is at least one instance where PQC is faster than classical, but that's a benchmark result. It gives you a guidance, but you have to test it within your own environment. And there are test harnesses that we have built that are freely available that you can go and use it in your environment to figure that out. So it is a factor that we pay close attention to because you want it to be better performant, if not definitely at least equally performant as classical. That's one. The second is how long are they going to hold good? The new math one of the things I said was, hey, we picked up one math problem, which is factorization, and said there is no solution for it. Let's go 100% down on it and create all algorithms based on that. Easy to do, started in 1974. 50 years later, it still works. This new one, we didn't want to put all eggs in one basket, so we have different math problems, hash-based, lattice-based, isogeny-based, multivariate quadratic equation-based, different math problems. So even if one happens to perform poorly or one happens to be broken in the future, you have something else to fall back to if you choose to do so. So I'm not saying it will never be broken because I cannot predict that, because some creative algorithm using quantum computer may come up, but in the event it does, we have other algorithms to fall back to.
Okay, thank you.
All right, thank you so much, guys. Enjoyed it.